Today we're going to talk about two types of magnetic fields in specific. The first one is going to be the B field of a long straight wire. So the B field of a long straight wire. Now, the reason that we say long straight wire is because basically we're going to have a wire and it's going to go like that. It's going to have a current going down it in that direction, and we're going to be over here in the middle, like somewhere in the middle of it, like a point like that. Okay. So basically we're going to have a length that goes along for a while. Okay. And we're going to have we're going to pick the contributions from just one little point on it. So our current is I. I'm going to write that down here. Okay. And we're going to have some little section here. Okay. That little section there. I'm going to find its contribution to our point over here. Okay. So it's along the y-axis, so I'm going to call this little section dy. And I'm going to call the distance between the wire and the perpendicular distance between the wire and the point over here. I'm going to call that distance x. Okay, and I'm going to find the contribution for that. We're going to use the law of Biot-Savart in order to find that little contribution, and that little contribution is going to be mu naught I dl cross r hat divided by 4 pi r squared. Okay. I'm going to go ahead and lose the r hat, only because if you look at the wire from where we're standing, we're going to get a contribution that's going to be basically perpendicular to both x and y. So if I'm on one side of this wire, if I'm on this side of the wire, I'm going to have if I use the right hand rule, I'm going to have a magnetic field that's going to be out of the page. That's the magnetic field on that side. And if I'm on the opposite side, okay, I'm going to have a magnetic field that's into the page on this side. Okay. That's going to be my contribution from the entire wire. And at this point, I'm going to have the same exact thing. So I'm not going to worry about that so much. I'm going to be much more worried about the other ones. Okay. So that means I'm going to go ahead and just reduce this to just the mu naught I. I redefine this as dy. 4 pi r squared. Okay, and you can see that r is going to be this distance here, which if I call this distance y, the distance between this point, the perpendicular point, and the point that dy is, then r is going to be mu naught I dy is going to be 4 pi. It's going to be the square root of x squared plus y squared, all squared. Now you notice I forgot that I'm going to do the sine of theta over here. Okay, should be an n maybe. Come on, maybe. There we go. Okay. Now, what's the sine of theta going to be? Okay, remember that's going to be our angle here. Okay, because it's IDL cross R, and that's going to be x times the square root of opposite over hypotenuse. So it's going to be x squared plus y squared. And then I'm going to gather all these terms together. I'm going to get mu naught I x dy over 4 pi. Oh, sorry, erase that. Because there's no point in writing both those things again. I'm just going to put both those things together. It's going to be just x squared plus y squared to the 3 halves. So I rewrote the actual segment of the magnetic field, and then we're going to actually have to integrate it. Okay, we're going to have again, remember the wire is going to be long, so basically it's going to be an infinite length. So to find the actual magnetic field, we're going to have to set limits from negative infinity to infinity of this whole expression, mu naught I x dy over 4 pi x squared plus y squared to the 3 halves. Okay, and you can see there's a bunch of stuff that we're going to go ahead and we can factor out. So it's going to be mu naught I over 4 pi. I'm actually going to leave the x with it. I don't have to. Negative infinity to infinity of mu naught, it's going to be just the pieces that are left that are relevant to the variables, which is going to be x dy over x squared plus y squared to the 3 halves. Okay, it's not the worst integral in the world. It's pretty doable actually, but again, I was lazy, so I went ahead and just took this whole thing and put it into Wolfram Alpha. And let's look at the results that look like. Hey, thanks Wolfram Alpha. So I typed it in right here. Oh, sorry. Okay. You can see that I typed it as x dy over x squared plus y squared, all to the 1.5 power to the 3 halves. And it wrote it nicely right here, and it gave me an answer of y over x to the root of x squared plus y squared. So let's go ahead and work that out. Let's do it right here. So we're going to have, and we have our limits too. So we've got mu, so b is going to be mu naught I over 4 pi, and we've got y over x squared plus y squared, and we have to use infinity to negative infinity. Well, let's take this and let's group it over here. Okay. And then let's take a look at this fraction at those two limits. Okay. Well, so what that means for us is that when we're looking at y is the variable we took with respect to, remember, is dy. So it's y we're looking at. So if y is really, really big, then this fraction is going to be basically y over the square root of y squared, which is just going to be 1, right? Okay. And at negative infinity, it's going to be negative y over the square root of y squared, which is going to be negative 1. So that means we're going to end up with the following. And I'm going to go to a second page to do it. So again, I'm going to rewrite that stuff. Mu naught I over 4 pi. Remember, I factored out the x. And my fraction is just going to be 1 for infinity minus my fraction for negative infinity, negative 1, which is going to be mu naught I times 2 over 4 pi x. When I do all that, it means that B is going to be mu naught I over 2 pi x. Okay, and that's exactly what we're looking for. That's the expression we want. If you look on an equation sheet, the one you usually find is mu naught I over 2 pi r, where r is going to be that perpendicular distance taken between the x value, or sorry, between the wire and the point that you're looking at. So that's the whole deal.